On April 28, 1988, at an altitude of 24,000 feet, a commercial airliner suffered a catastrophic structural failure. The resulting NTSB report recorded 1 fatality and 8 serious injuries. Until that moment, the flight was entirely routine. The aircraft was a Boeing 737-200, a proven twin-engine workhorse used by Aloha Airlines to shuttle passengers on short routes between the Hawaiian Islands. As the aircraft climbed toward cruising altitude, a massive section of the fuselage skin over the forward cabin simply peeled away. In an instant, 18 feet of the airplane's upper body separated from the airframe and vanished into the slipstream. The disappearance of the ceiling left passengers in the first several rows strapped into their seats, staring up at the open sky, exposed to frigid temperatures and the deafening roar of hurricane-force winds. Modern commercial airliners utilize fail-safe structures specifically engineered to prevent this scale of destruction. To understand how an airplane could shed its skin in midair, we have to look past the violent rupture and trace a hidden process of mechanical degradation that had been advancing for 19 years. To keep passengers breathing comfortably at cruising altitude, the cabin is pumped with air, turning the fuselage into a sealed tube with high pressure pushing outward. If that skin ruptures, the pressure equalizes instantly. The air escapes in a violent rush, called explosive decompression. The sheer force of that escaping air swept flight attendant C.B. Lansing out of the cabin. Meanwhile, in the cockpit, the flight crew fought to maintain control of a crippled, unaerodynamic airframe as it dropped through the violent headwind. Despite missing a massive portion of its upper body, the damaged structure held together just long enough for the pilots to execute an emergency descent and safely land at Kahului Airport on Maui. Getting the 94 remaining people on board to the ground alive was an extraordinary feat of airmanship. But the subsequent National Transportation Safety Board investigation focused strictly on the physics of the metal, determining the exact mechanism that allowed the fuselage to fail. To find the origin of the failure, investigators focused on a single horizontal line running lengthwise along the upper row of windows, known as the S10L lap joint. Evaluating the integrity of this joint requires looking at how an airframe ages. For a pressurized hull, chronological age in years is secondary to the number of pressurization cycles. Every time an aircraft takes off and pressurizes, the fuselage stretches outward slightly. Upon descent, it depressurizes and relaxes. Each cycle flexes the metal a microscopic amount, similar to bending a paperclip back and forth. A typical long-haul aircraft might log 1 cycle over an 8-hour flight. Aloha Airlines operated 35-minute hops between islands. By 1988, this specific airframe had endured 89,680 flight cycles, logging dozens of flexes every day. Mathematically, the aluminum structure was deeply exhausted, operating at a cycle count double its original design limit. This cross-section shows the Boeing 737 lap joint. Thin aluminum panels are laid one over the other. To secure this overlap, an epoxy-impregnated cloth was placed between layers. Rivets held the assembly tight, while the glue carried the load. In a controlled environment, this bonded joint spreads stress smoothly. But this aircraft had spent 19 years operating in the warm, humid, and salt-heavy coastal atmosphere of Hawaii. Over time, moisture infiltrates the microscopic gap between the metal sheets. This triggers crevice corrosion, a chemical attack that degrades the epoxy layer, causing the aluminum plates to physically separate, a process known as disbonding. The load-sharing mechanics collapse. 100% of the constant outward pressurization stress was transferred from the wide surface of the glue directly onto the mechanical rivets. The geometry of a single rivet hole reveals a critical weakness. It's beveled in a V-shape, so the rivet sits flush, leaving a sharp lower rim called a knife edge. Cabin pressure hitting this rim causes massive localized stress spikes, known as stress concentration. Because the epoxy bond had dissolved, the rivets were the only thing holding the panels together. Every single time the airplane pressurized, thousands of pounds of force hammered directly against these fragile knife edges, initiating structural fatigue. Under that concentrated stress, the metal begins to tear at the microscopic level. Tiny, invisible hairline cracks sprout outward horizontally from the sides of every single rivet hole in the lap joint. Investigators confirmed this by placing the torn wreckage under a microscope. They found fine parallel lines called fatigue striations, tiny physical ridges left behind in the metal, tracking the exact growth of the cracks cycle by cycle. Fail-safe designs assumed a single crack would hit reinforced tear straps and stop, but those straps had disbonded. Instead, dozens of independent fractures formed in a neatly aligned row. This multiple site damage turns solid metal into a perforation, like a ticket stub. The sudden loss of the roof was the mathematical conclusion of thousands of microscopic failures. On cycle number 89,680, that entire perforated line of fractures linked together, and the skin unzipped in a single catastrophic rip. This failure did not happen without warning. As a passenger boarded the aircraft in Hilo earlier that afternoon, she noticed a continuous crack running lengthwise along the upper row of rivets, the location where the structural separation later began. By the time fatigue damage is plainly visible to the naked eye on the exterior, the hidden internal network of multiple site damage is already nearing total failure. The National Transportation Safety Board concluded that the probable cause of the accident was the failure of Aloha Airlines maintenance program to detect the extensive disbonding and fatigue damage along the lap joint. While the specific vulnerabilities of these early cold-bonded seams were known within the aviation industry, the regulatory oversight and inspection protocols lacked the rigor to assemble those technical warnings into actionable maintenance for this specific airframe. The aircraft had been actively exhibiting the physical signs of disbond, corrosion, and advanced cracking. The ultimate failure was an inspection system that remained deaf to the visual language of fatigue. Flight 243 forced the global aviation industry to confront a massive structural vulnerability. The multiple site damage observed over Maui proved that thousands of pressurized jets worldwide were aging toward the exact same statistical breaking point. In response, regulators launched the National Aging Aircraft Program, mandating intensive physical inspections of high-cycle lap joints and overhauling oversight procedures across the global fleet. As this diagram shows, the industry moved away from the older assumptions of fail-safe design, pivoting toward damage-tolerant design. This requires engineers to assume cracks will inevitably form and require structures to be inspected so rigorously that any flaw is caught long before it reaches a dangerous size. The sudden disaster over Maui demonstrates that catastrophic structural failure marks the conclusion of a long, invisible process. Safety in complex systems requires engineers to assume the worst, seeking out microscopic signs of degradation and acting while the metal is still intact. If you value deep dives into the exact mechanics behind historical disasters, consider subscribing to the channel. We use viewer suggestions to drive our forensic reconstructions. Thank you for watching, and we will see you in the next investigation.